Hi, this is Miss Hubbard. I'm going to talk about Chapter 3 for the LMC section about chemical bonding for our Chem 7 class. So the most important thing to remember is that every element wants to follow the octet rule except for hydrogen and helium. They only want 2 electrons in their outer shell because they're small. But every other element wants to follow this rule. They want to have 8 electrons in their outermost energy shell. To do that, they can get rid of electrons or gain electrons, or they can physically bond with other atoms to make that 8 electrons in their outer shell. So the noble gases have this 8 electron octet. And so they're perfectly happy that way. They're unreactive. They don't form compounds with other elements because they have a full shell and they're not wanting to add, subtract, or combine with anybody else. They don't want to add any electrons, get rid of any electrons, or bond with anybody because they're perfectly happy with 8 electrons in their outermost energy shell. And so their octet is filled. Valence electrons are the electrons in the outermost shell, and every element has less than 8 except for that group 8 group. Group 8A, the ones on the very right side of the periodic table, have 8 valence electrons. And for example, carbon in group 4 has 4 valence electrons. All these 8 group elements follow the rule of their group number is their number of electrons in their valence, which is the electrons in their outermost shell. And we call it a shell or an energy level. So elements in group 1A have 1 valence electron. So as you see, we put in all the A elements here on this little chart for Lewis electron dot structures. And elements in group 1A have 1 electron in their outermost valence energy shell. So group 1A have 1 electron in their outermost shell. And so as you see across, all the A elements follow that rule. The A's tell you that their group number is the number of electrons in their outermost shell, or energy level. Remember, shells and energy levels, different words for the same thing. So we'll do practice problems in class. And let's talk about ions. Now some elements form ions because they want to follow that octet rule. They'd either like to get rid of some extra electrons and feel like their octet is filled, or they might gain electrons to make that 8 outermost shell. So if atoms lose, remember elements on the left side of the periodic table like to lose electrons, so I call them left are losers, and then the elements on the right hand side of the periodic table like to gain, and so the right are gainers. Elements on the left side are losers, and when they do that they become positive cations. Positive ions, which are called cations. Elements on the right-hand side of the periodic table like to gain electrons, and when they do, they become negative ions, which are called anions. So positive ions are called cations, and negative ions are called anions. So we see that for lithium, which is in group 1, this atom has 3 protons and 3 electrons. It has 1 electron in its outermost shell. It would like to lose that, so that when it does, it drops down to having a full outer shell, like helium does, and then it feels more secure that way. It likes to have that energy shell filled. So it's easier for lithium to lose 1 electron. And so you see it over here. It's become a positive ion on the right hand side. So it's become a positive ion over here because there's 3 positive protons, 2 negative electrons, and it's dropped 1 electron off, and it's going to give that to somebody else. So it's formed a positive ion. And we give it a symbol with lithium with plus 1 charge. So atoms on the right side are gainers. They gain electrons, and when they do, they become negatively charged. So fluorine is in group 7. He would really like to have one more electron in his outermost shell. And when he does gain that electron, he becomes a negative anion, fluoride anion. Remember, anion is negative. And he's gotten one more electron, so now you write him as fluoride with a negative charge. He gained one electron in that transaction. So here's the rules. Group 1s are going to want to give away an electron. Group 2s are going to want to give 2 electrons. Group 3 is going to want to give 3 away. And nitrogen will gain 3, sulfur will gain 2, and fluorine will gain 1. And so you can see what the charges are afterwards. So it's really important that you can just look at a periodic table and write down the charges for each group as soon as you look at the group number. So 1 is going to be plus 1, 2 is going to be plus 2, group 3 is going to be plus 3, 5 is going to be minus 3, 6 is going to be minus 2, and 7 is going to be minus 1. So when we talk about these things, we can also just use the electron dots, which makes it a lot easier. And we can say who's gaining electrons and who's losing electrons. So if you look here, sodium wants to gain 1 electron. Sodium wants to give away 1 electron. And sulfur has 2 holes that it would like to feel like it has 8 electrons for an octet. So for this to work out, we need to fill those 2 holes for sulfur. And so that means we're going to need 2 sodiums for this to happen. 1 electron is going to go here, and from the other sodium, 1 electron is going to go there. When that happens, sulfur has its octet filled, and it's gained 2 electrons, so it's now a -2 charge, so it's called sulfide now. And sodium has lost 1 electron for each one of them. So sodium is a plus 1 because remember, group 1 guys are going to be plus 1 elements. So they'll be cations. They'll be plus 1 cations. So when these ions go together, they bond in an ionic bond, and they arrange themselves so that the positive and negative charges are balanced out. So for this one, sodium is a plus 1 charge and chlorine is a minus 1 charge. So they're equally, just need 1 and 1 to make everything balance. So they arrange themselves in this nice little cube. So if you look at sodium chloride from your salt shaker, you're going to see that they're little cube shapes. So we'll do practice in class. Covalently, so ionic bonding is where electrons actually move from one element to another. Covalent bond is where those electrons are shared. So when 2 electrons are shared, that's called a single bond. There's lots of atoms on the periodic table that like to become bonded together covalently, and they like to do it diatomically. So diatomic means 2 atoms bonded together. So remember that Brinkelhoff thing I was talking about in class, Br2, I2, N2, Cl2, O2, and F2, Brinkelhoff, and H2 also. So all those guys like to be diatomic molecules. When they're bonding together and they're sharing electrons, it's called a covalent bond. And when they covalently bond together, they make a molecule. So here's some electron dot structures, and you see that fluorine has 1 hole right here. 1 hole that it wants to fill. So it's going to make 1 covalent bond with somebody else. Oxygen has 2 places that it can bond, so it's going to make 2 bonds. Nitrogen is missing 3 electrons, so he would like to hook up with 3 other atoms. And carbon is really unique. It would like to hook up with 4 different atoms, and so it's able to make really long, complex molecules because it likes to fill up all of those 4 holes and make 4 covalent bonds. So here's some of the structures showing bonding. We have, remember the Brinkelhoff people, they do diatomic. So H2 is a diatomic molecule, and each hydrogen has one electron, so they're going to share those two. That's called a covalent single bond. We can write it like this, draw it like this, or we can draw it like that with a single line. So one single covalent bond has sharing of two electrons. So here's one single bond, but here's a triple bond. We're sharing 6 electrons. And so you see a triple bond right there. And these electrons here are not bonding, so they're called a lone pair. You see them right there. They're not bonding. They're just hanging out on the end of that nitrogen. So they're called a lone pair. You see another lone pair here. And hydrogen wants to hook up with 3 things. So it makes this bonding. 3 single bonds. So we can draw them like this as well. And we still have that lone pair hanging out there. So lone pair means 2 electrons not bonding to anything. So we can predict what type of bond we have just from looking at the periodic table or looking at something called electronegativity. So if elements are really far apart on the table, they're going to make ionic bonds. If they're close together, they're going to make covalent bonds. If they're a little bit far apart, then one atom is stronger than the other one, is able to pull some of the electron cloud towards itself, and that's called polar covalent. I was talking about the analogy in class of sharing, when you're a little kid sharing a bed, and you have a big blanket over each other, and one kid's stronger than the other, and during the night pulls the blanket more over herself or himself, and that means that the electron cloud's more over that little kid, if they were atoms, and so that little kid's stronger, able to pull the blanket over itself. So that happens when 2 atoms are bonded together, but one's stronger than the other, and it makes a polar covalent bond. So we use these things called electronegativity numbers to figure out what is happening when these 2 atoms bond together. So when atoms are really far apart, they have really differences in that number. Lithium is a 1.0, fluorine is a 4.0. So when these bond together, they're going to be ionic. When elements are really close together, for example, fluorine and oxygen, their numbers are pretty close together, so they're pretty much the same strength. So they're going to be bonded covalently. What the problem is when they're kind of close together, maybe, fluorine and a selenium or something, we have to figure out, are they bonding polar covalently or just plain old covalently? So we use this little chart to figure out, well, let me show you this first. So, like I was saying, this guy, chlorine, is pretty strong. He's able to pull the cloud over himself a lot, and poor old hydrogen's pretty cold over here. The blanket's not over him too much. So the electron cloud is shown here. And most of the electrons are just hanging out here mostly. They're moving all around here. And not very much of the electron is going over the top of this guy. So on this bond, hydrogen is kind of feeling cold. So he's got a partial positive charge. And this side has lots of electrons around it, so it's partially negative. And we look at these electronegativity differences. 3 minus a 2.1 makes 0.9. So then we look at this chart and we say, okay, a 0.9 is somewhere in here. So this bond that we just showed you is polar covalent because we said it was a 0.9 difference. So you can use this chart to figure out, do I have equal sharing, which is called non-polar covalent? Do I have unequal sharing, that's polar covalent? Or is one so strong that he's able to take the electron from the other one? That's called ionic. So practice we'll do in class. And when these atoms bond together, they make shapes. So we need to think about the shapes, and then when they have a shape, we can also think about, is one side of the molecule polar, which has a slightly negative side, and is one side partially positive? We can figure that out by the shape. So when we can draw it like this, with these are electron clouds where the electrons are buzzing around inside the shape like little balloons. Or we can draw like this, where the central atom's like that, and then we show electrons in four corners. So these are equivalent to each other, just different ways of drawing the same thing. Just know that electrons like to stay as far apart from each other as possible. So if we have a central atom and four atoms bonded to it, it makes a tetrahedral shape. And so they'll show you like this. This is the way we normally draw things, but then we have to think, hey, in real life it has this three-dimensional structure. So it's got four bonded things to it. When a central atom has four things bonded to it, it's a tetrahedral shape. So this is really what it would look like if you were on the atom level. You could see it, that shape. Some atoms make a pyramidal shape because of this lone pair here. So this lone pair, instead of making this thing flat on the table, this lone pair pushes these guys down and it makes a pyramid shape. So this lone pair takes up a lot of space and it pushes these hydrogens down away from it and it makes a pyramid shape. Water is really unique because it has this bent shape to it. It's got two lone electron pairs and they push these two hydrogens down and it makes it into a bent shape overall. And that makes this side really slightly negative and this side slightly positive, and it makes water super unique, and really it likes to stick to itself, and that's really important for a lot of properties in science. Water is really unique. So we'll do practice in class. And so we can say overall, is a molecule have one side that's partially positive and one side that's partially negative? If it is, it's called polar. And polarity has to do with those bonds, whether one atom is stronger than the other, and also the shape of the molecule overall. That is what we were just kind of showing you with that water. That water molecule is polar. It's got one side that's partially negative, one side that's partially positive. So polar is kind of like, you think of the North and South Pole. They're different from each other. Same thing with water. We've got a slightly negative side and a slightly positive side, so those are the poles of the molecule. So here's a little chart of some, it's telling you about the bonds within the molecule, the shape of the molecule, and the polarity. So if you have non-polar bonds and your shape, the molecule is non-polar, an example would be this, methane. So non-polar bonds makes the molecule nonpolar, if all the bonds are nonpolar. If you have some bonds that are polar and everything's symmetrical, then the overall molecules could be nonpolar. So for example, this C to Cl bond is polar, but because this is tetrahedral in shape, those bonds make the overall molecule nonpolar. If you have polar bonds and there's no center of symmetry, it's not a symmetrical molecule, then that whole molecule is going to be polar, and that's what I was showing you on the water. So we'll do practice in class, and I think that's it for Chapter 3. So please take a look at that. Most important is ionic and covalent bonding, and the polarity of bonds also. So the beginning of this chapter is the most important. Thanks for listening. Bye now.